In this video, we're going to talk about elimination reaction, which we use a symbol big E. There are two types of elimination, just like there are two types of substitution reaction. And these two types of eliminations are E2 mechanism and E1 mechanism. So what you are seeing on the screen is the mechanism, example and the mechanism of E2 reaction, which primarily occur to primary or secondary alkyl halide. In this example, this is dehydrohalogenation reaction, which is basically eliminating a hydrogen and a halogen atom from an alkyl halide. Now, usually the reactant is an alkyl halide. See, this is a pentane group, and there's a bromide, and the presence of base and under heating, and this is what's going to happen. Now, where the halide is going to be the leaving group, similar to the leaving group in the substitution. Now, in this case, the bromide is going to be leaving with a pair of electrons. The carbon that bromide is directly attached to is so-called alpha carbon. And next to alpha carbon, there are two other carbons. Now, these carbons are beta carbon. So we can quickly label them so we can see. Makes it easier for we to talk about it. So this carbon, where the leaving group leaves, is called alpha carbon. Now, in this case, this alpha carbon is a secondary carbon, so it has two beta carbons. Now, of course, assume there are hydrogens attached to the beta carbon, so this hydrogen is called the beta hydrogen. So this kind of elimination is also called the beta elimination. And what's going to happen is the base, which in this case is the hydroxide, one of the lone pair on the oxygen is going to pick up this hydrogen. So in other words, this hydrogen is considered to be acid. It's an acidic proton. Of course, acidic proton can be neutralized by a base. Now, when the proton leaves, the electron goes back. Now, this electron is not going anywhere. It's going to form a double bond between the alpha and the beta carbon. Now, when the alpha-beta carbon bond, pi bond is formed, alpha is going to let the bromide go. So bromide is going to be the leaving group. Now, the hydroxide is the base. The outcome is that the bromide is left as a leaving group, and hydroxide has been neutralized by the proton, forming water. The hydrogen, one of the hydrogen used to be on the beta, is the beta hydrogen. And there's a alpha-beta pi bond being formed. Now, with this mechanism, we can see there's a possible transition state when the beta hydrogen leaves, but not completely, partially left, and alpha-beta bond is partially formed, and the leaving group leaves in the halfway. So the transition state will look like this. Sorry. Trying to get the pen back. So the transition state is the leaving group has not left yet, and double bond is partially formed, and the hydrogen has not completely left yet. And the base is partially bonded to hydrogen. This is the transition state. Now you can see everything happens at the same time. Two things: leaving group leaves, base picks up the proton. So there's only one transition state, but this transition state is a bimolecular mechanism. Therefore, it's called the E2 reaction. You can compare this to SN2 reaction. It's kind of similar mechanism, but I want you to appreciate the difference. Usually in the substitution, the lone pair directly attack the carbon that leaving group leaves. But here, you're actually attacking the hydrogen on the beta carbon, not the alpha carbon directly. One thing we're going to understand is that you have to choose, when you know there's an alpha carbon, which beta, when it has more than one beta carbon, which beta carbon is going to be react, or in other words, the double bond is going to be formed between these two alpha beta carbon or between the other alpha beta carbon. This is called the residual selectivity. Now we can learn a basic rule, which is called the Zaziv's rule. Zaziv's rule says basically something we've learned before. The double bond, which is going to be the product of the elimination, with more alkyl substituents, or in other words, with more C's directly attached to the double bond, will give it more stability or higher stability of the compound. In other words, we prefer to form a double bond with more substituents. Now, with this in your mind, you might be able to think about when you have different choice of double bond to be made, which one is going to be. There's one thing more before we go to the next slide. It's worth to mention that is the elimination reaction prefer to use strong base and heat, which we're going to talk more about this in the next few video. Here's an example of so-called residual selectivity. Now, if you look at the first example, here's the chloride, which is potentially a leaving group. So this is the alpha carbon. In this case, there are two beta carbons. Their possible hydrogens can be react with the base, which is a hydrosulfide. Hydrosulfide is just like hydroxide with a lone pair. Under heating, the hydrosulfide is possibly to pick up one of the beta proton, and this chloride will be leaving at the same time. Now the question is it going to be on A or B? Because if you choose A, the double bond will be on the right side. If you choose B, the double bond will be on the left side. You can only do one. The outcome is you might get both products, which is double bond on B and double bond on A position. Now if you compare these two products, B has more substituents compared to A double bond. So B is going to be the major product. In the lower example, we're using a different kind of base, which is a T-butoxide. It's a T-butyl attached to an oxygen. This is also a very strong base. Now the reactant has iodide on this carbon. So this is alpha carbon. Again, there are two possible beta carbons. They both have hydrogen. The lone pair on the oxygen can potentially pick up one or the other one. If you pick up the one on top A, then this pair bond, the beta hydrogen bond, will flip over to form the double bond. Or if you choose pathway B, the beta hydrogen bond down here will form a bond, which will result into A and B. Now if you compare A and versus B, you will find both A and B has the same amount of substance around the double bond. Therefore, there's no preference. And that's why you get a 50-50, the mixture of two products. Now you can pause the video here, see if you can draw the reaction or even possibly a mechanism of the following reactions on the screen. Now the first one, the leaving group is chloride, and the alpha carbon is here. It looks like there are two possible beta carbons, but you should be able to see that the beta carbon onto the left, a highlighted in red spot, has no hydrogen. So that's not even a possibility. The only choice, it seems like there are two choices, but really the only one choice that's valid, which is the terminal beta carbon. So the oxygen hydroxide lone pair will attack this hydrogen, and this hydrogen, the bond, the electron will come to form a double bond between the alpha and beta, and the chloride will leave. The product is going to be and of course chloride. That's a negative. The second one is using T-butoxide. The T-butoxide is actually going to be attack this alpha carbon. The bromide is going to leave. To this alpha carbon, there's only one possible beta carbon, which does have a hydrogen. So T-butoxide will pick up this proton, and this hydrogen, the bond used to attach to, is going to turn to a bond between alpha beta carbon, and alpha carbon will lose the bromide. So the product is going to be, the 6-member ring stays exactly the same. There's nothing changed. Now between beta carbon and alpha carbon, the bromide is going to be gone, but there's going to be a new double bond between alpha beta carbon. On the third one, you're looking at an alkyl oxide or ethyl oxide, which is again a base. You can see the reactant, there's a iodide, which potentially can be a leaving group. The carbon bonds to the iodide is the alpha carbon. There are two possible beta carbons, one on top, one to the left or right, left or lower. They both possess hydrogens. So the oxide can potentially pick up one or the other one. When the proton is picked up by the base, the bond will be flipped over to form a double bond between alpha beta or the other side. The leaving group leaves as iodide. Iodide will be the leaving group. The product is going to be, we're going to copy the exact same structure. Now this is the alpha carbon and the beta. So there's a possible product here. Or there's another possible product with a double bond here. Now you can see between these two products, there's no preference because they both possess two substituents on the double bond. So this is going to be 50-50%. Now in the test, if you believe there's a major product, write the major product only. If you believe there are two possible products with equal opportunity, then you should draw out both structure or both products. The next one is going to be another elimination, but with a different mechanism. This is E1 reaction. Most of the time, you would only have tertiary alkyl halide to undergo E1 mechanism. The E1 mechanism relative to E2 mechanism is because this is going to be unimolecule mechanism. You can see this is a tertiary of bromide. This is going to be the alpha carbon. Now, this is just like SN1 reaction. The unimolecule mechanism, there's always going to be a carbocation intermediate. With a positive charge. And that's what's going to happen here. Because of tertiary carbon, it will be very hard for base to attack the alpha beta carbon. Therefore, the bromine will just leave under heating, which will result into a carbocation intermediate. Now this intermediate is going to be fairly stable because of the tertiary because it is a tertiary carbon. Now of course, with a positive charge here, that will make all of the beta carbon or beta hydrogens particularly acidic. When the base present, the base will pick up the beta proton, and just like in the E2 mechanism, when the base picks up proton, this pair of electrons will flip to the alpha beta double bond, resulting into a new double bond, but at the same time, the bromide is gone. Now, of course, if you look at the other beta proton, you might be able to form another product with double bond at different location. Now, similarly, because you have two methyl groups here, so the third beta proton down here, if you take the proton away, you're going to form double bond down here, and that's going to be the exact same product as the second one. In this case, through E1 mechanism, we're still following the Z-Stiff rule. The products with more substituents will be the major one. But you have to understand that for any rules, there might be exceptions. There might be other factors has a bigger impact than just the stability of the double bond. But that's not what we're going to discuss here. I just want you to keep in mind what we're learning here is just the basics of some reactions. But don't be surprised in the future if you see any exceptions. For now, or for this course, I think it's just understanding that there's a possibility you might have to choose which product is going to be the major one if you can have different products.